Welcome to Verilog Lesson 5, Gate Level Modeling. Understanding this fundamental concept is crucial for aspiring chip designers and engineering students. Today, we'll explore how circuits are described using basic logic gates, a core aspect of chip design. Gate level modeling is a low-level approach, much like building intricate structures with Lego bricks, where each brick represents a basic logic gate. Verilog provides built-in primitives for these gates, offering a direct correspondence between your logic diagram and the Verilog code. For instance, an AND gate combines two inputs to produce an output only if both are true, implemented simply as AND in Verilog. Similarly, an OR gate outputs true if at least one input is true, coded as OR, while a NOT gate inverts its single input, written as NOT. In these examples, the first terminal listed is always the output, with all subsequent terminals serving as inputs. Real-world gates aren't instantaneous. They have timing delays, which Verilog allows us to model precisely. We can specify a rise delay for transition to 1, fall delay for transition to 0, and turn off delay for transition to Z, using syntax like and number 5. Gate-level modeling plays a critical role in the digital design flow, particularly after synthesis. RTL code is transformed into a gate-level netlist by synthesis tools, which is then verified through gate-level simulation, also known as SDF simulation. This simulation accounts for timing information, ensuring the design functions correctly post-synthesis. To summarize, gate-level modeling uses basic logic gates, and Verilog provides primitives for these. Crucially, timing delays can be accurately modeled, and gate-level netlists are essential for post-synthesis simulation. Thank you for watching this lesson on Verilog gate-level modeling. We hope this has provided valuable insights into chip design. Don't forget to subscribe for more Verilog lessons, and stay tuned for our next topic, data flow modeling.